还真买了一个。
你给我们买
就一个小水杯，那我就觉得太小。
太小了，那么小不用喝的，没有。对，
你这真可爱。你先拿过好吧？我让那个等会儿。
这个小水，这个太小了。这不做吧？这没有。
水果。你这边，一个是不停的让你们，是现在这个做平，好几个在加在，两个四三零。这个咱们调理没那么做。
All right. So, welcome to the last lecture for EC 5882-6882. I'm going to finish the rest of the lecture on analog amplifiers, and then I'm going to, after that, solve the questions, exercises for the previous lectures, including the PLL, the filters, and the analog amplifiers, also the assignment 2, and some hints about the final exam questions. So any questions before I start? All right. So just so if I want to give you a brief on what we followed last week. Just here, because we have lots of things to do. I don't want to spend much time on this, but we talked about the analog amplifiers, especially the op amps, so voltage feedback op amps, and now we are going to cover the current feedback and the instrumentation amplifiers. So the voltage feedback op amps, the block diagram is like this. I mean, we have two inputs, and then the output, the model is the AO, which is the open loop gain, multiplied by the difference voltage between the two inputs, and then we have a finite output impedance. So this is the block diagram of a voltage feedback amplifier. The values that you can find in the data sheet about these parameters, for example, for the open loop gain, I believe most of you have designed your analog amplifier for the design project, so the values for the open loop gain is something between 80 dB to 200. Here it is mentioned 80 dB to 100, but I believe up to 200 dB also available. Then another parameter, important parameter, is the gain bandwidth. So gain bandwidth is frequency dependent, and it has, for example, for the model we put a nominal value, but when we increasing the bandwidth, the gain drops. So, for example, if the gain bandwidth of an amplifier is, I don't know, 100, it means 100 megahertz. It means that if we have a gain of 10, then the maximum frequency that we can cover with this amplifier is 10 megahertz. But it's not like that. I believe it's less than 10 megahertz, because when we are reaching to the constraint, which is the gain bandwidth, the product gain bandwidth drops. Another value is the output impedance or output resistance, which is in the order of tens of ohm. For example, 50 ohm, 10 ohm, 20 ohm, something like that. Based on this amplifier, if we look at the conventional method for designing an amplifier based on the voltage feedback amplifier, you can see that we have two types of circuits, the inverting and non-inverting. They are almost similar. Both of them we use negative feedback, and the difference is just to the pin that we apply the input pin, the input signal. So if we apply the input signal into the negative input, then the gain is negative. If we apply to the positive input, then the gain is positive. And then the gain is calculated, depends on the ratio between the feedback impedance to the input impedance. After that, we covered the stability of the voltage feedback amplifiers. So the stability of the voltage feedback amplifiers, we said that there are three phenomena that can make an amplifier unstable. First of them is the load capacitance. I mean, if we have a capacitive load, then it can result in instability of our circuit, because then the closed loop gain has another pole, and if this pole is in the region of interest and in the bandwidth that we are working at, that bandwidth, then it can change the phase margin, and it can leads to the instability. So we saw this example that, for example, for the LF347, if we have different types of capacitive loads, for example, 100 picofarad, 1 nanofarad, or 5 nanofarad, then increasing the capacitive loads can shift the pole into the lower frequency and probably into the our operating region. So based on these values, you see that we can have poles at the frequency of 50 megahertz, 5 megahertz, or 1 megahertz. And higher capacitive load means lower position of the pole. Another component which can lead into instability and again generate a pole inside the working region is the inductance in a feedback path. So if we have a LS, and then again we draw the circuit model for this circuit and find the open loop and then open loop transfer function, we see that again we will have another pole, and then this TL or tau L will come from this formula. Again, we see that if the value for this L increases, then this T increases, and then the position of the pole could be in our working region. Also, from this formula, you can see that by increasing the gain of the amplifier, we can, this is one method that by increasing the gain of the amplifier, we can move the pole into the higher frequencies, out of our band. So we have two methods to compensate for this L. One is increasing the gain, another one is reducing the L. So increasing gain and reducing L can help for make this circuit again stable. And the third one was the input capacitance, input straight capacitance between the two inputs, inverting and non-inverting inputs. If there is a capacitance between these two, again, if we draw the circuit model for this, we reach into this formula, and again you see that we have another pole. So this is the pole which is generated by this capacitance or capacitor, and this is TC, and then this TC is calculated based on this formula. In this structure, you see that the gain does not help that much. Increasing the gain does not help that much to move this capacitance to a higher, the pole to the higher frequency. But again, if the capacitance increases, the pole position decreases. This is what you should consider. And then we introduce a method, a compensation method, to get rid of the effect of these three parasitics. The output capacitance, the input capacitance, or the inductance in the feedback path, and that's a capacitance in the feedback path. So if we have a capacitance in the feedback path, it will generate a pole and a zero. And then we can tune this capacitance in such a way that the zero that it generates compensate the pole which is generated by the parasitics, and then the pole that it generates be, for example, far away from the operating frequency. This is how it can help us to compensate the effect of the parasitics. The value for the zero and the value for the poles are coming from these two formulas, and here is the example for that. For example, we have a capacitive load of 200 picofarad, and then the output resistance of the AD818, which is a good op amp. It has a almost gain bandwidth of 100 megahertz. It's for most of the AM applications. It's useful. And then this load and this resistance gives you a time constant of 1.6 nanosecond. And then this 1.6 nanosecond is in the order of 100 megahertz, which is in the range of the frequency that this op amp supports. So to get rid of that, we can, for example, use another capacitor to make a zero again exactly at this one, and then this capacitor is 1.6 picofarad. So 1.6 picofarad capacitor in the feedback, I mean here. So if we put a capacitor here, and the value is 1.6 picofarad, then this capacitor will compensate, I mean, it generates a zero in the transfer function, which compensates for the hold which happens due to the load capacitance. And then it will generate another pole. It itself will generate another pole. This is what I mentioned here. So it has one zero and one pole. So this zero is for compensation of the pole coming from the parasitics, but it itself generates another pole. But the pole is in higher frequency. I mean, it's in 200 megahertz. So if we look at these graphs, what does this graph say? So the main thing in the stability of an amplifier, always we should look at the phase margin of the amplifier. For example, at the operating frequency of 100 megahertz. If you look at the operating frequency of the 100 megahertz, at 100 megahertz, or assume 50 megahertz, because 100 megahertz, the gain is almost around 0 dB. I mean, this is the point that, which is the cutoff frequency of this amplifier. So at 50 megahertz, if you look at the graph, you see that without So I think this is because the phase margin drops in this one, while when we add a feedback, I believe this is not plus feedback, this is plus up amp plus the capacitive load. And this is also up amp plus the capacitive load. So you see that when we add the feedback, the phase margin, for example, at 50 megahertz, it is 45 degree, and without the compensation. But when we add the compensation or the feedback, then we will see that the phase margin increases, for example, to 60 degree or 70 degree. This is how it helps for the increasing the stability of the amplifier. So I think this is now correct. And the gain, if you see, the gain does not change that much. I mean, with the feedback or without the feedback, the gain does not change that much, but the phase margin improves. I mean, the phase margin. So phase margin, higher is better or lower? Higher. So when we are, what does phase margin means? Means the amount of phase that we allow our circuit to, or our load apply to a circuit, and then the system is not going to get unstable. If by adding a load to this system, then the phase, because of that load, the phase of the system, for example, drops or lags by, I don't know, alpha degree, then it means that if our phase margin is less than that alpha degree and then it drops to the zero, then the system is going to be unstable. So higher phase margin, it means that we allows a more or higher range of loads to be attached to our system, while our system is not going to be unstable. So this is what we covered last week. The new section is about the current feedback amplifier. So the current feedback amplifier, the block diagram is like this, that the output voltage is dependent on the input current. I mean the current which is passing through these two pins, not depends on the voltage difference between these two. So each current feedback amplifier defines by its R in, and then the R out, it has a R out, and then the transfer function, I mean the gain of, so this is the gain of the current feedback amplifier, is ZS, which is dependent on the frequency. I mean this is a kind of impedance. So the impedance, but the impedance which is dependent on the frequency. ZS multiplied by the input current. And then the V out is coming out of that. Again, we say that in the current input amplifier, I mean, we say we do a kind of similar analysis with the current feedback amplifiers, the same analysis that we have for the voltage feedback, because we again assume that the V plus and V minus are almost the same. Why? Because the V plus minus V minus is I in R in, and then if we assume that this current is very small, then we say that the voltage plus and voltage minus are almost similar, and then we do the same analysis that we have in the voltage feedback. And why we can assume that I in is almost equal to 0? Because this ZS is very high, and then this V out is limited. So I in, which is equal to R out divided by R out plus ZS I in. So as this ZS is very high, and this, sorry, this is V out. So this is limited, and this is very high, and then we say that this I in is almost 0. Okay, again, okay, what we've done here, when we want to analyze a voltage feedback, we have to do this. So this is the criteria that we find the open loop gain of an amplifier. We need to do two things. One, to first short circuit the input source. I mean, we remove the input source, and then we break the feedback loop, and then we find the open loop gain of an amplifier. So here again the same thing we apply. So again this short circuit the input, I mean we say that the V equal to 0, and then we open the feedback loop here. I mean we open the feedback loop here and then apply the signal at this point, V test, and then we find the V out over V test to find the open feedback. And then if you've done that, then you will see that the AL equals to this value, the open loop transfer function. All right. So here, so this is a current feedback op amp. So this current feedback op amp, again, we have the baud diagram, and then this baud diagram shows amplitude of Z. So this is actually is volt divided by ampere divided by 1 ohm. So this is the amplitude of Z in dB. Okay? And then the phase. I think the phase is this side from 0 to 90. So the open loop feedback depends on the RF, and then, for example, for the RF equal to 300 ohm, we can see that, all right, the gain bandwidth is at this frequency, and then the phase margin is this value, and then the open loop gain amplitude is this value. One thing that you have to consider, okay, here, when we find this equation, we assume that these two are 0 or are small. So this is important that, okay, this is a very simplified version of the open loop gain. But if we will see in one of the examples that if we assume that the R in is not 0, then what we found for the transfer function is a bit different. I mean, it's like this. So the I in, then we don't say that the I in equal to 0. So I in has we have a value for the I in, and then based on that, the transfer function is different. In here, in this formula, you see that if we increase the value for the K, then okay, I can say that this one is reducing, the effective feedback gain is reduced. This one is comparable to RF. I mean, this value is comparable to RF. Then the effective gain is reducing. In the graph, in the data sheet of this IC, if we assume that, for example, the small value for the RF, for example, to 37 ohm, and then if we assume that the input impedance is 20 ohm, then the effect of the Rin is small if K is small. But then if the K increases, I mean, if we have a higher gain, then the effect of the Rin is not negligible, and then the bandwidth will be reduced. So by increasing the K, I mean, for example, if the K is less than 10, then definitely this is 1. It's fine. But if by increasing the K, then this value is important, and then the bandwidth will reduce. This is just a topic on the current feedback amplifiers, and although the operation is a bit different, I mean the definition is a bit different, the internal circuit is different, but the analysis is almost similar to the voltage feedback amplifiers. And the number of current feedback amplifiers in the commercial shelf is much, much less than that for those which is voltage feedback amplifier. Another one is the instrumentation amplifier, or those that we are using for differential loads. I mean, if we have a differential load and we want to measure something with those, then we use an instrumentation amplifier, and then we use a filter, and then after that we try to amplify the signal. I mean, these instrumentation amplifiers has a high common mode rejection ratio. So the common mode rejection ratio for these are, for example, in the order of 100 dB or more. And because of that, then the signal that we apply into the plus minus, because of that common mode rejection ratio, we can have a signal here. I mean, it's not going to get saturated. And then after filtering the signal and then amplifying the signal, we can detect the signal. They are very useful as a first stage for the instruments, for example, the ECG or EEG signals. So here we have two probes on a body, and then these two probes are applying to the positive and negative pins of the instrumentation amplifier. After that, we put a filter. So the instrumentation amplifiers, I mean, at this stage, we do not expect a high gain. So if we want to amplify our signal, then we use another amplifier to apply a gain. For example, you see that the gain here is just 7, but then if we want to have a higher gain, to make it a value which is acceptable by your A to D, then we have another amplifier to increase the gain. You can see that the common mode reject ratio for example, AD620 is 100 dB. So the common mode reject ratio is important for the instrumentation amplifier. Also, similar to the other op amps, it has a voltage noise source and current noise source, and the values are significantly small, 9 volt and 0.1 picoampere per square root of hertz. How we are going to connect our amplifiers to a load? For example, if we have a sensor that the output of the sensor is capacitor, then how we can measure the capacitance of this sensor by using the amplifier. So this is the method that we are going to use so we apply our capacitor or our variable capacitor, which is coming from our sensor. So our sensor output is a kind of capacitive load. So we connect this capacitive load into the input of this op amp, and then we use another capacitor to make the gain, and then this is the filter. This is the first order filter that we had, and also we can get a gain out of that as well. If our input, for example, so the applications for this is accelerometers. So accelerometers output are capacitive. And then if you want to measure that, you can use this circuit. For the resistive sensors, then like the thermal sensors, thermal resistors, or pressure sensors, or the photodiodes that the output is resistive, then we can use again this structure. I mean, we use the resistor as the input, and then this one for the feedback, and then another stage just for the gain and filtering. So if you remember from the assignment 1, the problem, what was the problem with this structure? That we have two capacitors, and then what was the problem with that? And we had two capacitors like this in an op amp. What was the problem with the noise?
The noise that goes out is based on this input capacitor that we have,
And it was high.
over the
Because of the 1 over F noise, which is the dominant noise at the low frequency, then because the impedance or the impedance of this capacitance at the very low frequency is very high, then the amount of 1 over F noise that we achieve in the output is very high. So, and most of the sensor applications are working in low frequency, I mean in the order of hertz or I don't know, tens of hertz. So to get rid of this problem, then we are using a modulation. Okay, what we do? Assume that we have a capacitor like this. I mean, assume that we have one sheet here, then another sheet here, and then another sheet here. So I call this sheet A, I call this sheet C, and I call this sheet B. Okay? And then by applying the actuator voltage, then the position of this sheet is, I mean the sheet C is moving. So we have a capacitor here, I call it the C1, and we have a capacitor here, I call it the C2, and then by applying the actuator voltage, the position of the sheet C is moving in such a way that if the C1, for example, increases, the C2 decreases. Okay? So I write down the C1 and C2 in this way. So you know that the C equals to epsilon A over T. Okay, and T is the distance between two sheets. All right. So we have this C1 and C2, and then they are like this. The C0 as the whole capacitance, the total capacitance, and they are in series. So the total capacitance that we have is 2 C0, and then C1 is C0 plus, so I can say that the C1 plus C2, which are in series, then it is 2 C0. Okay. So I applied a voltage V1 cosine omega t to one of them, and exactly the same voltage but in opposite phase to the other one. Okay. So the voltage at this point, I mean at this VC, equals to this value. I mean equals to VC. And then I put just a unity gain amplifier. So this is a unity gain amplifier. I mean the voltage at the point C and the voltage at the point D are equal. So VC equal to VD, and then it is equal to this one. Why? Why it's equal to this? So when we want to find the voltage at this point, we have to use a superposition. I mean, I say that, okay, here is ground. I mean, point A1. A is ground. B equals to minus V1 cosine omega t, and then find the voltage based on that. And then 2, B is 0, and then A equal to V1 cosine omega t. Okay? And then find the voltage at the superposition of these two. And then you will see that this value based on the C1 and C2. So the voltage at this point, for example, for the second, I just say that the voltage at this point, the V of C equals to VB multiplied by the Z of C1 divided by Z of C1 plus Z C2. Okay? And then for the other one, the same. This is just VA ZC2 divided by ZC1 plus Z, and then the superposition of these two. So this is the VD. And then if I use a mixer here, and then this mixer is again working in the same frequency, I mean, I use in the same frequency, then the output will be like this. Okay? I mean, I multiply this VC. So the output of the mixer is VC multiplied by V or VD multiplied by V naught cosine omega t, and then this VD is also, it has two components, one which is in the frequency of 2 omega t, and one which is at DC. Clear? So these two has two components, one high frequency, one low frequency. So the high frequency, I get rid of the high frequency with this low pass filter, and then the low frequency is just this. So this is the V naught multiplied by V1 delta CT divided by 2 C naught, and then another 2, which is the 1 over 2 of this one. So this is equal to 1 over 2 of something. And then cosine phi. So you see that in the voltage output, we can see the effect of the delta C. I mean, how the C is changing, we can see it in the output. But we are working in the frequency of the omega, not in the DC. And then we can get rid of the 1 over F. If you look at the spectrum, so this is the spectrum of the capacitive sensing. So capacitive sensing without modulation, I mean with the normal sensing, if we are looking at the noise, so the noise is like this. I mean, we have a 1 over F noise in this region, which is very high, and then this is the 1 over F noise corner here, if you remember from lecture 2, and then this is the thermal flat noise of the circuit. But when we are doing the modulation, because of this low pass filter that does not let because of the modulation that moves our signal to the higher frequency, then the noise that you see is like this. Because it modulates also the noise. And then the noise that we see at low frequency is like this. So modulate, actually this is a very simple circuit, so lots of research is going on this. I think Professor Mehmeti himself, his group is working on this. Many more complicated circuits on this has been designed and tested here in Monash. another noise that usually we have to deal with in our sensing applications is the noise which is coming from the AC lines or the 50 hertz. Again, by using this modulation in a frequency which is higher than the 50 hertz, then we can avoid those as well. Okay, I think this is the end of the lecture 12. I'm going to solve questions for, I think, lecture 9. We didn't go through that. All right. So for the exercise 1, so it says that we have two sources of clock 40 kilohertz and then another clock 41 kilohertz, and then we apply those two into XOR. So what's XOR? What did we use? No, I mean that what's the application of the XOR in a PLL? What's the application of the XOR in PLL? Is it VCO? Is it phase detector? Is it filter? It's phase detector. Okay, so this is our phase detector. And this is our filter. So we apply two signals with different frequencies, but almost, very close to each other, 40 kilohertz and 41 kilohertz, to one phase detector, and then put a low-pass filter. I want to see that, okay, what's the output for this? So I've done this in a LT Spice. If we can connect, hopefully. Okay, so we have two signals, the V1 and the V2, okay, and then one of them is One of them is 40 kilohertz and the other one is 41 kilohertz. I set the signal like this, and then if we run this, if we see, so this is the clock 1 and this is the output for clock 2. You see that, okay, it starts to get shift, and then again, for example, they get in phase and then out of phase and so on. And then I apply these two into a XOR gate and then put a filter here. So the output of the XOR is like this. You see that, for example, in the first cycle. So in the first cycle, the overlap between these two is small, and then it gets higher, 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 and then again, when they got the phase shift is around pi, then again it drops. The duty cycle of the XOR out. And then our output will be a kind of triangular shape. So this triangular shape, if you remember from the lecture 9, was something that we had here. So we apply two signals, almost similar signals to this one, and then put a low pass filter. So the voltage at the VC is like this. Now our loop is open, but we assume that the frequency that we can apply at this point is very close to the reference frequency. I mean, our VCO is working in the correct region. It's not very far away that it goes out of phase and it cannot lock. So we assume that our frequency is very close to the reference frequency, and then the output of the phase detector and the low pass filter then will be like this. Depends on what is the initial different phase between these two, then you will see a value, a shape like this. Okay? All right, for the question 2, so it's mentioned that we have a XOR gate from this family, 74HC, and then the voltage supply is 5 volt. So it changes, I mean, your output is changing from 0 to 5 volt. When the supply of it, digital logic is 5 volt, it means that the output is changing from 0 to 5 volt when it is HC CMOS, high-speed CMOS. So then it says that find the relationship between the phase error and output of the phase comparator, and then find the KD. Okay, KD, we say that, all right, so if you remember from the previous question, that if we have a signal like this, depends on the for example, this is V1, this is V2, and then I apply this V1 and V2 into a XOR. So this is V1, this is V2. And then the output of this is changing. So here is 5 volt. So the output of this is changing from to pi, and then again to 2 pi. This is what we had in that graph as well. It means that the gain of this XOR KD equals to then the 5 volt divided by pi, which is equal to 1.59 volt per radian. So this is for the first part. And then in the second part, it says that, okay, we have a VCO which is working at 25 kilohertz, and then the gain of the VCO itself is 5 kilohertz per volt. Okay. So first, design a low pass filter which gives a rapid response, means rapid response with little overshoot means zeta equal to 0.7. Okay. All right. So first of all, it says that the KO equals to 5 kilohertz per volt. Okay. But our KD is in radian. So we have to change this to radian or change this to hertz, either of them. So if I want to change this to radian, it means that this is equals to 2 pi 5 kilohertz per radian. Kilo radian per volt. So this is kilo radian per second, which equals to 31.4 K radian per second. Okay. So this is the first thing. If you remember from the lecture, if I go just back, yep, here. So for the first order filter, we had this formula that the zeta equals to 1 over 2 square root of tau 1 kd ko. And then from this we know that what's the value for the zeta, which is 0.7, and then what's the value for the kd, what's the value for the ko, and then we can find the tau. And then based on the tau we can design our filter. Okay? So why it's mentioned here second order, but I said that the first order filter. Why first order filter leads to second order system? Where is the other pole? We have a system like this. This is a first order. But why this is second order? Because of? Yeah, because VCO also has one pole. Okay? So first order filter leads to second order system because the VCO is like this. It has one pole. So based on this formula, then we can find the value for the tau 1. And then we can say that the tau or tau 1 equals to 1 divided by 2 kd ko. Remember that the theta equals to 1 over square root of 2 tau 1 k dk. And then from here we found tau 1 equals to 10 microsecond. Okay. And then what's the low pass filter? The low pass filter is just a simple R and C, and then the tau 1 equals to 1 over, tau 1 equals to RC. Okay. So you pick a value for the R and then find the value for the C. For example, R equal to 1 kilo ohm, or then 100 ohm, and then find the value for the C based on this. And then it says that find the value for the lock range of the PLL. What's the lock range of the PLL? Okay, lock range of the PLL. So we had the center frequency 25 kilohertz, and then if we look at this graph, it means that when it is 25 kilohertz, it is at this point. It is at the 2.5 volt. So 2.5 volt of the, output of the VCO equals to 25 kilohertz of the frequency. So then it can move 2.5 volt down, 2.5 volt up, and still we can lock it with this XOR system and low pass filter. So the range that we can do the locking is 25 kilohertz plus minus. All right, and then the KO itself is 5 kilohertz per volt. Okay, so 1 volt of change is 5 kilohertz. And then now we can change 2.5 volt. So plus minus 2.5 multiplied by 5, which is, this is 12.5. So it can lock in the range of 12.5 kilohertz to 37.5 kilohertz. So this is the lock range of the VC. 25 kilohertz is the center frequency, so it is in the middle, and then we can lock 2.5 volt down, 2.5 volt up, and then the VCO itself is working like this. For every 1 volt of increase, then it moves, for example, 5 volt, or every 1 volt of decrease, then the output frequency decreases 5 volts. So we can lock in this range. But out of this range, then the phase is totally different. If we move, for example, to this region or to this region, and then it's not going to get locked. I think this is it clear? Is this question clear? Okay. All right. For the filters, so we have few designs for the low pass filter and band pass filters for different type, for example the Chebyshev, the Butterworth, and then the different orders. So in the first question it says that design a low pass filter, LC low pass filter, and the cutoff frequency at 12 megahertz, and then the RS equal to RL equal to 50 ohm. It doesn't mention that, okay, what is the type you can set, for example, take it as Butterworth or you can take it as Chebyshev. Here the circuit will be like this. I mean, we have a source, so this is our source, and then we have this RS, and then we can either start from the capacitor or inductor. For example, if we start from the capacitor, then the filter, the fifth order filter will be like this. And then finally this is our load. We say this is C1, this is L2, this is C3, L4, and C5. So we want to design a fifth order filter, and the RS equal to RL equal to 50 ohm. If we go to the table for the Butterworth, so Butterworth with equal terminations. I mean when the RS and RL are equal. And then the fifth order one, then these are the coefficients. You should consider that when the RS and RL are equal, the coefficients are symmetric. I mean, for example, this one and this one are the same. These and these are the same. Okay? It doesn't matter. Also, we can start from the C. We can start from C to C1, L2 to C5, or we can start from L to L, for example, L1, C2. And then the graphs could be different. I mean, when we start from the C, it's like this. When we start from L, it's like this. Okay? The result is the same. All right. So from the table, we can see that the G1 equal to 0.618. Is that correct?
Yeah.
Okay. And then so I can say G1 equals to G5 equals to 0.618. G2 equals to G4 equals to 1.618, and then the G3 equals to 2. Okay. So based on this, then we can say that C1 equals to C5 equal to G1 or G5 divided by 2 pi FC multiplied by R, and R equals to R here equals to RS equals to RL. 50. So if you calculate this, and then the FC is 12 megahertz, then this value is 163.92 3 picofarad. And then the L2 equals to L4 equals to G2R divided by 2 pi FC, and this is equal to 1.073 microhenry. And then the C3 equals to, again similar to the first one, it's G3 divided by 2 pi FCR, and is equal to 530.52 picofarad. Okay, so this is the first part. In the second one, it says that design a third order Chebyshev bandpass at the center frequency of 10 megahertz and then the bandwidth of 2 megahertz. So it is mentioned that it should be third order, and then these are, but it doesn't mention the ripple. I think it is missing ripple, and the ripple is 1 dB. Ripple better than 1 dB. All right, again RS equal to RL. So we are going to the table for the Chebyshev filters here, and 1 dB ripple. So third order filter, and then the RS over RL equal to 1. So again you see that this is symmetric because RS equal to RL. Alright, so these are the values, and then if I want to, okay, I just draw something and then go back in. So the band pass filter will be like this. I mean, this is our ES, and then again we can start from a capacitor or inductor, no difference. So I start from the capacitor, and this is the inductor. So this is C1, L1, C2, L2, and C3, L3, and then our load. So this is our RL, and this is RS. So this is the shape of our filter. Again, G1 equals to G3 equals to 2.216, and then the G2 equals to 1.088.
series, but balance.
Yes. Thank you. Okay. And then we are following the formulas for the bandpass filter. So for the bandpass filter, these are the formulas. For the parallel components, we have to follow these, and then for the series components, we have to follow these formulas. Okay. So then the C1, what's the formula? I don't have it here. Equals to G1 divided by 2 pi RB, and B is the bandwidth, and then the L1 equals to RB 2 pi F naught squared or FC squared G1. Is it correct? Correct? Yeah. And then the C1 equals to point 353 nanofarad, and then the L1 equals to 0.718 microhenry. And actually this is equal to C3, and this is equal to L3 as well. So what's the formula for C2? L2.
RG2 over 2R.
And this one is 585 picofarad, and then for 33 microhenry. Which one? This is third order. So fifth order, then you have to go, or seventh order, then you have to go to the table and then find the values for the seventh order. For example, here we are solving for 1 dB rebel. So fifth order, then these are the. So C1 equals to C5. L2 equals to L4, and then C3 is different. For the seventh order, the same. I mean, this one and this one are the same. This and this are the same. This and this are the same. Okay. No difference. So the last question actually is third order Butterworth. I think it's quite similar to the question number 2. I will upload the solutions. You can follow that. The same formulas you can use. The only thing you need to check into the Butterworth with the equal terminations and find the coefficients. Okay? Any question on this? Clear? All right. The next question is about the Salin and Key low pass filter. So it says that find the values for this R, C3 and C4. I mean, design this filter in such a way that it is a second order filter and it has a natural frequency at 15 kilohertz and a zeta of 0.44, which equals to a Chebyshev filter with 2 dB ripple. So these two are equal. So in the filter design, the omega n and zeta, I mean the specific values for the omega n and zeta can translate into the type of the filter and the ripple that we will achieve in our passband. Okay? So we have if you remember from here, from the Salin and Key, this formula and this formula, that when we define Salin and Key, if we write down the transfer function of this, then we are reaching to a second order transfer function, and then based on that we can write down that the zeta is a square root of C4 divided by C3, and then the omega n is 1 divided by R, a square root of C3 C4. So apply these two into these two values, I mean, if I mention that r square root of C3, C4 equals to 1 over 2 pi 15 kilohertz, which is 10 to the power 10.6 microsecond, and then we have the square root of C4 divided by C3, which is equal to zeta equal to 0.443. So we have two equations, three unknowns. We select one of them and then calculate the other two. Okay, we pick a number for one of them and then calculate the other two from these two formulas. So I assume that, for example, R equal to 4.7 kilo, and then based on those two we can find that C3 and C4 equals to 5.07 nanofarad and 1 nanofarad. In the second question, it said that, okay, assume that instead of this second order filter, we have this passive second order filter. I mean, this is a first order filter, this is a first order filter, and then we cascade these two, it's a second order filter. Similar to first order filter in cascade. And then at the end, we wanted to compare the transfer function of these two to see that, okay, which one is better. If so if I want to first, it says that, okay, find the transfer function of this one. If I want to find the transfer function of this one, if I assume that the current here is I1 and the current here is I2, then I can write down that the V in equals to Rx I1 plus 1 over S Cx I1 minus I2. So I write a KVL here, and then if I write a KVL here, then I can say that again 1 over S Cx multiplied by I2 minus I1 plus Rx plus 1 over S Cx I2 equal to 0. And then I know that V out equals to 1 over S Cx I2. And out of these three, I mean, I find the I1 here and replace it here, and then I found the V in based on I2. I know that V out based on I2, and then I can find the V in based on V out. Okay? Then we can see that, and then if we assume that the Rx Cx equals to tau, then we can find that the V out divided by V in equals to 1 plus 1 plus 3s tau squared s squared. So from the equation 2, find I1 based on I2, replace it into the first one, find V in based on I2, V out based on I2, and then we can find the V in based on V out. Okay. So this is the graph to compare these two. Okay. So this is the graph for the just the two cascaded first order filter, and this is the graph for the Salinan key, I mean the red one. So you can see that, okay, at the end of the band, because this is Chebyshev, and we have Chebyshev, we always have overshoot, or we have ripples. So you can see that we have a 2 dB ripple in the passband for this, but we don't have any ripple for this. But for example, this frequency, I mean the cutoff frequency of this and the cutoff frequency of this are different. The rate of transition from the passband is much faster for the Chebyshev comparing to, for example, two cascaded second order and first order filters. So this is actually moving very slowly, but this is a kind of sharp, but with the expense of the ripple in the passband and then overshoot at the end of the band. Okay? All right, and then the last question, which is very simple, it says that, okay, what does this circuit do? So if you remember from the lecture, so we have two clock signals, one of them the X1, one of them the X2, and they are non-overlapping. I mean, then if this is the X1, and then this is the X2, and then we apply them to these two switches and these two switches. So this is X1 and this is X1, this is X2, X2, and then we have 4 switches and then 3 capacitors. So this block and this block are switching capacitors block. So what's the circuit equivalent for this? It's a resistor. So we can say that, okay, this is a resistor, this is a resistor, and the value of the C1 and C2 are equal, so the value for the resistors also are equal. And then the R is equal to 1 over the C F, and F is the frequency of the clock, or F of S, F of sampling. Then this circuit is simplified to this circuit, that we have a V out, V in, R, and then this is C3. What's this circuit? What's the circuit? Band pass filter, high pass filter, low pass filter. Yeah, this is low pass filter. So if you want to see that, okay, what does it do? Just put S equal to 0, S equal to infinity. See that what will happen. Okay. So this is a low pass filter. And then the transfer function of this, so V out divided by V in equals to minus, alright, one thing that I forgot, that, okay, then this one is equal to 1 nanofarad, 10 to the power minus 9, and then the frequency of the clock is 1 megahertz, 10 to the power 6, and it is 1 kilo ohm. Okay, so this is equal to minus Z2 divided by Z1. So Z2 is this 1K in parallel with 1 over S C3 divided by 1K. And then if we apply the value C3 equals to 10 nanofarad, so C3 equals to 10 nanofarad, then we will see that it is equal to 1 divided by 1 plus 10 to the power minus 5 S. This is a low pass filter. What's the gain? What's the gain of this filter? $10, $200, 10 to the power 5, 0 dB or 1. So the gain is 1 or 0 dB. So the AV of the DC, actually at DC it is 1 or equal to 0 dB. Put S equal to 0 at the DC. S equal to 0. Okay. So we can have a few minutes break, and then we continue for the last lecture questions, and then the questions for assignment 2, and some hints on the exam questions. And then we will check the SETU to see if we can have a quick lecture next week or not. And then, yeah, it's all. This week. No, I didn't upload it. I will do it this week. I didn't find time actually. I will upload the part that I saw that my voice is there, but there is no video. Okay, I will record again. All right.
Yeah.
In the report just mentioned that who did what.
So the thing is, like, we still have 2 days. So the thing is, if he can't fix it, what do you suggest? Should I start building it from scratch? Should I show you some of the stuff work already? Should I just need a bit of compensation from you?
No, if you've done your part, done. Just write your report.
But he tried really hard. So it's not his fault.
I know that it's not his fault, but I mean, he can upload his file and he can upload, for example, everything that he has done. It's fine.
Can we just, show you the design quickly?
Yeah, I can. Actually, the other lady showed me something. I already gave her some comments on that.
Is there any between which will be available in the lab?
Tomorrow, 5 to 6. Yeah, tomorrow and Friday also.
有啊，
这不是每个人都把这个20吗？
All right.
16是这样的，没有结果他最后还是平的。
对，翻译系统。
我去，
但是我发现他
我来
他就一个点，他
去了。
做完的就是不一样。
做完啥？
做完啥？做完。我做了，因为我都失声了都已经，我声音都变了。
不想跳了。但没题目，只有概念点，没有题目。有在 lab， 在 lab 里就再说4S那个都一起答。对啊，我是缺兴趣啊。那还不是你自己把电脑放这么会写？他们的东西就没有他们的算了。 点点嘛，啊呀，我发誓，抹不就我不就也有这种地方，突然抹就怎么抹？我来打分。我们先打，先下课。哦，不好意思，看不出来。不好。然后再从一个两个没事，他什么都不在跟我说，真的是他一个是一个下打完加了屁股，下面加一排，就算你先把那资料给我高。设计一个里面东西，你跟我说的。你又在这？哦，是啊，我觉得这个因为我吃。原来比那个啥。要改动的话，对，我不改，改对呀，你是知道吗？在不在？加上。
Okay, shall we continue? So one thing that I forgot to mention here, so if you look at the transfer function of this filter, I showed a comparison between the Salena and Chebyshev filter and then two just cascaded first order filters. If we look at this in more details, so we can write down this is like this. I mean, it's 1 over tau squared plus 1 3 over tau s plus s squared. Okay. And I think it's in the order of, it's in the shape of omega n squared, s squared plus 2 zeta omega n s plus omega n squared. Okay? Yes, you are right, sir. Okay. So from this, we can understand that so omega n equals to 1 over tau. Guys, be with me. So omega n is 1 over tau, and then the zeta equals to 3 over 2. What does it mean? So zeta equals to 3 over 2. What's the response type? Is it underdamped, overdamped, critically damped, overdamped? So and you saw in the figure that how slow was that. So it is overdamped because the zeta is greater than 1 and the transition is so slow. So this is one thing that I wanted to mention. Any question on this filter? No? Okay. So in the analog amplifiers, so the questions actually are connected. All of them are based on one amplifier, which is the CLC 401, and it's a current feedback amplifier. So it says that the output resistance of this amplifier is 20 ohm. So the R out equals to 20 ohm. And then the input resistance of the amplifier R in equals to 50 ohm. And then it says that, okay, the ZS you can find in the graph in the data sheet. And then it says that, okay, find the expression for the open loop gain. All right. So for the open loop gain, we said that we short circuit the source and then cut the loop and then look at this one. If here is V out, then the A of open loop equals to V out divided by the V test. Okay. So what I can write down is that from the current feedback amplifier, we know that the V out equals to Z of S I in. Okay. If you remember, the shape was like this, that we had a buffer here, we had R in, so this is R in, this is the buffer, and then here is V minus, here is V plus, and then we had a current source here, and then a resistor and ground. So this resistor was RO, and then here was ZS I in. here is V out. This is the circuit model for the current feedback amplifier. Okay. So if RO is very small, then we assume that this is correct. So here our R out is 20 ohm only. So then the V out is ZSI in, and if we again write down here like this, I mean if I write down this structure for the so this is R in, and this is RF, and this is RG. So I can say that this V minus, okay, this V minus equals to R in parallel with RG, because both of them are connected to ground. Okay, so it is R in parallel with RG divided by RF plus R in parallel with RG V out. Clear? Is it clear? So these two impedances, I mean this RG and this R in parallel, and then we have this RF in the feedback. So it's just the V out divided, I mean this one divided by the total. Okay? So this is one equation, this is one equation, this is the second one, and then also we know that the current which is passing here, and I call it I in, so I in equals to minus V minus divided by R in. Okay. So if I replace the V in to this one, then I can see that V minus to this one, I can see that it is minus 1 over R in multiplied by 1 divided by RF divided by R in parallel with RF plus 1 V out. Okay. This is time. This one. So if you look at the values here, for example, the R in is 50 ohm. So 50 ohm, for example, in parallel with, sorry, this is RG. This is RG. R in parallel with RG. So I just divide the top and bottom with R in parallel with RG. So if you look at this, any value for the RG higher than 50 ohm, then the R in is dominated. Okay, and then the RF over R in is a big value. I mean, because this is 50 ohm, for example, this is in the order of few kilo ohms, and then this is dominated. And then I can say that, okay, this is much higher than 1. So I can simplify this to minus 1 over R in, and just keep this one R in in parallel with RG divided by RF V out. And I know that the V out is ZS I in. And then from here I can say that the HS equals to R G divided by RG plus R in 1 over RF ZS. When we want to find the HS, we have to open here and then write those things. So this is the approximation formula if we assume that this is correct. I mean RF divided by R inside. If we look at the data sheet, so this is the data sheet. And then in the data sheet, so we have two things which are important. One of them is this board diagram, which shows the ZS. So this is the ZS. So I cannot write here, I think, but here this is the ZS in dB. The phase and the gain. So this is the gain and this is the phase. And then the exact formula for this one is like this. So it does not, I mean, this is what we had before. So it does not simplify this R in. So we have this. So this is the exact formula for the open loop gain. I mean, VO over VI is this one, and then the LG is coming from here. All right. In the second question, it is mentioned that, so now for the different values of the RF and gain, then what will happen for the bandwidths and maybe the, based on the board, what's the open loop transfer function and bandwidths, the gain and bandwidths. So if we put RF, for example, in case A, if we put RF equals to 1.5 kilo ohm and gain is equal to -1, then we can say that RG is also 1.5 kilo ohm. Okay. And then from this formula, and the Rn is 50 ohm. The Rn is 50 ohm. Then I can say that the HS equals to 1 over 1.5K plus 50 ohm ZS, which is ZS divided by 1.55K. So this is the HS. And then it says that to find the bandwidth. Find the bandwidth means where the open loop gain is 0 dB. So if I write down this in the dB format, for example, I say that this HS in amplitude in dB equals to this ZS amplitude in dB minus this one, minus 20 log of 1 over 1.55K, which is equal to, so So this value is equal to 68.3. I mean, this equals to in dB minus 63.8. Sorry, 63.8. Okay, so this is the transfer function in dB. So where the open loop gain equal to 0, when the ZS is 68.8 dB. Okay, so this is how we can find the bandwidth. So we are looking into the point that the ZS equal to 63.8, and then at that point we find what's the frequency. So if we look at the both diagram here, so here 63.8 is something like here, this one, and then the gain is here, and then coming down it's, for example, 150 megahertz. Okay, so 63.8, and then it's 150 megahertz. So I can say that the bandwidth in this case is around 150 megahertz. With this value of the gain. With this value of the gain, and in current feedback amplifiers, depends on what is the value of the RF. It could, I mean, we can have a gain of -1, but with another value of the RF, the bandwidth is different because this is important. This Rin is important. Rin, this is what I mentioned just here. I mean, when we are going to higher gain here, when we are going to higher gain, then if this Rin is not negligible, sometimes it could be, because the value for the RF, if decreasing, then the gain bandwidth changes. I mean, with the RF equal to 1.k and gain of -1, we get this bandwidth. But if we change this RF, for example, to 1k and still gain is -1, then it's changing. The bandwidth is changing. So for the B, the same thing. We put the RF equal to 1.k, and then the gain is -10, then the RG equals to 150 ohm. Okay, so when RG is 150 ohm, then again, if we put it here in this formula, then we can say that then this HS equals to ZS divided by 2K. This time it's 2K. I mean, this is 200 ohm, and this is 10 times of this. This is 2K. And again, if we follow the same procedure here, then it means that it is equals, I mean, HS in dB equals to ZS in dB, this time minus 66. So to find the bandwidth, again we put the 66, so it's here, and then the gain, for example, drops to, the bandwidth drops to around 10 to the power 8, 100 megahertz. So I can say that then the bandwidth is 100 megahertz. For part C, if RF equal to 5K and gain equal to -1, again RG equals to 5K, and this time HS equals to ZS divided by, what's the value? If RG equal to RF equal to 5K and Rin equal to 50 ohm, it's divided by 5.05 K, and then HS in dB equals to ZS in dB minus 74.1. So 74 is about here, and then, for example, it's here, it's around this 40 megahertz, for example. So bandwidth equals to 40 megahertz. So this is what I just said. We can have a similar gain, but the value of the RF is different, then the bandwidth of the system is different. So here is 40 megahertz, here is, I don't know, 150 megahertz, 150 megahertz. Okay. And then in D, we can say that again RF is -5 kilo ohm and gain is -10, then RG equals to 500 ohm and HS equal to this time ZS divided by, what's the value? RF is 5K, RG is 500 ohm, and Rin is 50 ohm. 5.5K. So this is divided by 5.5K. 0.55 multiplied by 10. And then the HS in dB equals to ZS in dB, this time minus 74.8, which is almost similar to the previous one, and I can say that the bandwidth is 40 megahertz. So what we can conclude from here is that when the RF is high, I mean, it does not matter that what is the gain, okay? What's the gain of the system? The bandwidth is almost similar when RF is high. But when RF is low, like this, then it does matter that what's the gain of the system, and then the bandwidth is changing. So this is what we can conclude here. Another thing is that, again, when RF is high, comparing to the RF is low, if the gain are equal, but depends on the value of the RF. If RF is high, then that Rin is negligible. if RF is low, then RN is not negligible, and it has influence on the total bandwidths. So here the gain is -10, but for one of them the bandwidth is just 100 megahertz, and in this case bandwidth is 40 megahertz. All right, in the last exercise it says that, okay, assume that we have a gain of -1. I mean RF equals to RG. It says that Y, the value, for example, for 2.5 kilo ohm is the recommended impedance for RF and RG. I mean, this is the optimum or the best one. Again, I write down this to see that what will happen when we put the RF equals to RG. So if we have RF equals to RG equals to 2.5K, then we can say that the HS equals to ZS divided by what was that? $2.55K. Is it clear that Y it is 2.55? Okay. I just put RF and RG 2.5 and RN is 15. And then from here the HS equals to ZS minus, can somebody calculate this? 20 log of 1 over 2.55K. Nobody has calculator? 20 log of 1 over 2.55K.
Minus 68.
ZS minus 68 dB. So if we look at the graph, so 68, for example, is almost here, okay? And then we say that at this point, so what's the frequency? Bandwidth is around 100 megahertz, okay? So if we look at the 68 and the gain, so it is around 10 to the power 8, okay? And then what's the phase? So the phase at 100 megahertz is around 60 degree, okay? So the phase margin is 60 degree at 100 megahertz. The phase margin is 60 degree, and the gain is 68 only. 68 dB. So at this point, then I can say that the bandwidth is around 100 megahertz, but the phase margin is almost 60 degree. So what does it mean 60 degree? It means that if I add a load to this system, and then because of that load I have a lag, but this lag is just below this 60, then 60 degree, then my system is not going to be unstable. We can go to a higher value. I mean, I can go, for example, to, I don't know, for the higher phase margin. I mean, I can go to, for example, this point, 120, which is very good. But the problem is that if I go to this 120, then at 120 you can see that what's your gain? Sorry, 120, excuse me, 120 is here, then you can see that, okay, your bandwidth is very small. I mean, if you look at this graph, so the phase in this region is almost similar. I mean, the phase in this region does not change that much, but the bandwidth is changing a lot. I mean, from this point, for example, the phase margin is 80. This point, the phase margin is 100. 20 degrees just I add to this system. But the problem is that at this point, the bandwidth, for example, is this point. The bandwidth at this point is this point. Okay? So it is not recommended that we lose this much of bandwidth because of only 20 degrees of phase margin. But a point here, I mean, when we are showing a kind of sharp transition in the phase, it's better to have our system, for example, in such a way that we are not losing bandwidth a lot, but also we have a good phase margin. In the systems, we say that we are designing system for always the phase margin greater than 45 degree, because below 45 degree, it is very probable that your system be unstable by a very simple parasitic. So we are trying always to design our system in such a way that the phase margin of our system be higher than 45 degree. So because of that, we say that, okay, 2.5K is a good number because it gives us a phase margin of 60 degree, and also the bandwidth is not that much reduced. If you go to higher bandwidths, I mean, for example, if we go to the bandwidths of 10 to the, I mean, at this point, here, at this point, then you see that your phase margin is almost zero. And it means that if you design a system at this point, it is unstable. It's totally unstable. The next question is that what would be the value for the RF equal to RG, and then the system will be unstable. What does it mean? It means that I have to find the first point here, I mean this point, which, I mean at this bandwidth, this is the point that we are almost unstable. And then at this bandwidth, I have to look at the gain. So the gain is around 55. Okay, so for the gain of 55, I almost get a phase margin of 0 and my system will be unstable. So if I write down this, that the ZS equals to 55 dB system is unstable. And from here we can say that our RF equals to RG is around 560. It means that any value to select, if we want to have a unity gain amplifier, just a buffer, and if we select any value below this for the RF and RG, then our system will be unstable. So then last part is that, okay, if we have a L, so this is our system. So this is RG and this is our RF, and it says that if we have a track and then this track generates, I'm connecting the V minus to V out on a PCB with a track. So if this track is long, any length, so it generates L. So this L can make your system unstable. So it says that if this track is producing a inductor 6 nanohenry per centimeter, every 1 centimeter 6 nanohenry, then what should be the PCB lengths that cause this system unstable if we select the value of the RF equal to RG to 2.5K. So when we are at 2.5K, so if I just, so I said that when we are at 2.5K, so we are here. So if we want to be unstable, then we have to move to here, from the 68 dB to 55 dB. Okay? So this is what we just found. And based on this formula that we had for the series this one. So if we have a series inductance in our feedback path, then it gives you something like this, and then this TL equals to LS 1 plus K R in, and then we have to find this LS in such a way that it generates that amount of loss in your open loop transfer function. So if I write down that, it means that the TL should equal to 20 nanosecond. Where did I find the 20 nanosecond? So my bandwidth is 100 megahertz and my R in is 50 ohm. So I want a pole exactly as 100 megahertz. So that pole, then the TL is 20 nanosecond. So this 20 nanosecond, and then it says that the L should equal to, I think, 80 meter. So if the length of your track is 80 meter on the PCB board, then your system will be unstable. Okay? That will not happen, never will not happen. Okay? All right. I think this is the end for this lecture. I just give a quick solution on the assignment 2. I don't want to write it. I solved it here. I show you the okay. So for the assignment 2, it says that find the Z in for this circuit in such a way that C pi and C mu are not negligible. I mean, we have a feedback from the output to the input. So what I've done is that I divided the circuit. I mean, I replaced the C pi and R pi in parallel as Z2. I put C mu as Z1, LE as Z3, and then the output loads in parallel at Z4. Okay, so then we can simplify this circuit into this one. So we have this Z1, Z2, Z3, and Z4. Just consider that this RE and CE are negligible in the high frequency or in the small signal model analysis. Okay. So I write down one KVL in this part, I mean the KVL in the first part, and then based on this KVL, so this is the KVL, I said that, okay, V in minus this Vx, which is this one, so this is, I assume that Vx, V in minus Vx plus the current that we have here, I1, minus I1 Z3 equal to 0, and then based on that, I know that this I1 equals to this current plus this current, and both of these two currents are dependent on Vx, so I can just write down the first equation, V in, based on the Vx. Okay? And then I write down another KVL in this loop, and based on that, again, I found the V in based on Vx and V out. Sorry, Vx and I in. Vx and I in. So in the second question, I write down the V in based on the just I in and Vx. And then from the first one that I found the Vx, I replace it in the second one, and then I just find out the V in based on I in. Done. And then this is the formula. So this is a big formula, but we can see something out of this. The first thing is that, so the Z in, when we don't have the C mu, if we don't have the C mu, which is the Z1, so if we don't have the C mu, then you remember that the Z out, I mean the Z out, the Z in does not depend on what we have in the collector. Okay, but when we have this C mu, then this Z4 is always important for the value for the Z. Also, for example, the GMZ4. So this value, most of the time we can say that this is 1. Why? Because the Z4 that we select here, I mean, if we selected the LC and CC in such a way that they are resonating at their at our operating frequency, then the only value which remains here is RL. And then most of the time this RL is a transistor. And that transistor, when we are looking into the emitter of that transistor, the impedance that we see is 1 over Gm. And then 1 over Gm multiplied by Gm is 1. So this is another thing that we can consider. So in the, for example, IC design, we usually don't have any R in the chip. All the R are manufactured and fabricated by transistors. So, and the transistor is, when you are looking into the emitter of a transistor, the impedance is 1 over G. The second part here, so we have the parameters. So we do have the parameters, and then he said that we need to design a matching. So for design the matching, first we need to find the GM and R pi. So GM and R pi based on the biasing. First you have to do the biasing for this, and then find the values for the IC and IB. So when you find the value for the IC, then we can say that, okay, what's the value for the GM, and then what's the value for the R pi. Okay. And then based on that, we find the values for the Z1, Z2, Z3, and Z4, and then the value for the Zin. Finally, the value for the Z. Okay? So this is correct if we assume that, okay, these two components, I mean the CC and LC, are resonating at the operating frequency, and then the RL is 50 ohm. So I pick a value for the LC and then find a value for the CC. All right? And then to do the matching on the Smith chart, so we have a Zin, and then we want to match it to a 50 ohm. I mean a 50 ohm at center. So if first we have, the first thing for the Smith chart is to normalize. So I assume that it's the characteristic impedance of my transmission line is 50 ohm. Then this is the normalized value for the Zin, and the normalized value for the Zs is 1. So I need to move from point A to the center, which is our source, or point S. So we have two ways to do this. We can go to this circle G equal to 1 and then go to the center, or we can go here to G equal to 1 and then go to center. So we have two ways to do this. I picked the first one. Why? Because the second one, if you pick the second one, I mean if you pick this circuit and then you put it here in your matching network, so the series capacitor is going to block your DC voltage, okay, and then your transistor is not going to bias. If you select the second one, you should make sure that you apply your voltage here, I mean your bias here. I mean move this bias here and then put the second circuit. Else it's wrong. I mean it's not, I mean your transistor is not working. So because your transistor is not get biased. No VB we have here, no IB we have, okay? And then based on the values that we got, I mean I moved from the point A to the point B, and then the XL I found is 0.55, and then at the frequency that we have, it is 438 nanohenry, and then the same thing for the capacitor. I've done another solution for this, which is more comfortable for computer-based programs based on the networks. I mean, how we can solve this in the network instead of writing KVL, KCL, and then I've done it in Mathematica. So it's much easier. For the computer, it's much easier. But the calculations by hand is difficult because it's matrix-based. So what I've done, I said that, okay, this circuit I set as one network, this circuit one network, and this circuit one network. So what I have to do, so I have network 1 and network 2 in series. I mean, you can see that these two are in series. So, and then cascade with network 3, and then find just the Z11 of the whole network. So that one is the Z in. So the Z11 of the whole this network is Z in. So the network one, so there are few steps that we have to follow. First, we have to find the H matrix of this one. It is available in your book, and we have it in our lecture notes. So the H matrix of the first one we have to find. And then we need to change the H matrix to the Z matrix for the N1, and then find the Z matrix of the N2, add these two together, then add the Zx equals to Z1 plus Z2. Again, change this Z matrix to ABCD matrix, find the ABCD matrix of N3, and then when they are in cascade, just multiply the ABCD1 by ABCD2, and then change the ABCD total to again Z matrix, and then look at Z11. So you can do this simply in the Mathematica, and it's just few lines of codes. So I've done this, so I found the H, and then actually I didn't find this, Mathematica found this. So then we find the Z for the network 1, we find the Z for the network 2, and then we add those two Z networks. I changed the Z to ABCD, and then find the ABCD for N3, multiply those two, and then again change it to Z, and then the equation is like this. I assume that we have RO as well, but if we assume that the RO is infinity, then it is exactly the same as what we found by the KCL and KV. Okay. Is it clear? No. Okay. So if it's not clear again, I can explain it again. Which one is not clear? The network part, or from the beginning? Network part. All right. So network, we say that any network can be defined by the currents and voltages at the input and output. And based on that, which current and voltage we are looking at, we have different network parameters. For example, Z parameter, H parameter, ABCD parameter, or Y parameter. Okay? And depends on which one is more useful in our circuit, we can pick one, and then we can transfer them to each other. I mean, if we have the Z parameters of a network, then we can simply, by the table, we can move to the ABCD. Or if we have Z, we can find the Y. Or we have H. All of these are transferable to each other. Okay? Here I said that, okay, this is a transistor. And transistor, we said that in our lecture note, we said that transistor, the best model, simplest model for a transistor is the H model. So because we can write down, for example, H11 as the input impedance, H22 as the output, H21 as the transfer function, and then the H12 as the isolation. So these are the values that I calculate for the transistor. And then we have another network which is just a simple impedance here. Okay? And another network which is again another, it's a simple impedance here. I found the network, the H network for the first one, and then I see that the network 2, which is this one, which is this simple ZE, is just a cascade in the Z parameters. So I need to change the H parameter of the first one to the Z parameter, and also calculate the Z parameter of the network 2, which is a simple Z. The Z parameter of this is Z, 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 Z. I mean Z, E, Z, E, Z, E, Z, E. the matrix. Input, transfer, output, and the backward, all of them are ZE. It's simple. And then add the Z parameters of these two together, and then I have the Z parameters of this part, the whole thing, the X part. Then this network, this new network, which has again one port here and one port here, is cascaded with the network tree. As they are cascaded, in cascade we are interested in ABCD. Then I need to change this network, the Z parameters of the network X, to the ABCD matrix. I found the ABCD matrix of this, and then I found the ABCD matrix of this. Again, it's simple. It is available in the lecture note, but it's the ABCD matrix of a simple load, okay? Which is this one. I mean, the Z matrix of a simple load is this one. 1, 0, 1 over Z, L1. And then I multiply the ABCD matrix of these two to find the ABCD matrix of the whole thing. And then I just change the ABCD to the Z matrix. And then we know that the Z11 is the Z in of our circuit. Okay? It's easy to do it with computer based. So in literature, when we have a big network, we do it always like this. I mean, we are writing the parameters for an individual parts, and then we write it inside a program and to find the whole matrix, and then we are looking at the parameter that we are interested. Okay. I think this is the end of our unit officially. Two more things are remaining. First, the exam. So for the exam, we have 5 questions. Okay. So I will write down this because I don't want you to get confused. At the end of lecture 11, all right. Final exam. We have 5 questions. You have 2 hours to solve the questions. And you have 10 minutes at the beginning to read the questions only. Okay? So these 10 minutes is very important. Just make sure to read the questions carefully first, because there are 5 questions, and then the question 1, Q1 and Q2, each of them has 15 marks, and they are compulsory. Okay? Question 3, question 4, and question 5, each of them has 10 marks, and you have to solve only 2 of them. Okay? Out of these 3, you have to solve 2 of them. And if you solve 3 of them, then the best 2 will be marked. So the last one I will not consider. All right? I mean, don't solve all the 3 and then get 30 out of that and then say, I mean, get 20 out of that and say that, okay, it's done. Okay? So optional only answer 2 of them. Okay? 2 hours is enough for the exam, provided that you answer only 4 questions. So because of that, I said that, okay, this part is very important. In these 10 minutes, try to decide that which 2 is more comfortable for you. And do not try to mess around and then go solve half of that and then come back and see that, okay, is it difficult, and then come back and solve the other one. Okay? So in this 10 minutes, in the 10 minutes, which is, I think, enough, just decide that, okay, which 2 is the best for you, and pick that and solve. Okay? The exam is open book, and open lecture note, and open notebook. And all of these has S. Okay? I mean, you can take anything that you want, okay, except your laptop and phone. Except your laptop and phone, the rest is allowed, okay? And also the calculator is any type of calculator you can take, okay? No, not important that it is, for example, Monash certified or not Monash certified, any type of calculator you can take. And because that the exam is open lecture note, I did not bring, I mean, there is no formula sheet for that. So you are supposed to take the formulas by yourself, okay? So, and the formulas are what is available in your lecture notes. I mean, if you read your lecture notes and read the exercises for the lecture notes and the assignments, and if you've designed your design project properly and understood that, I believe you will get 100 out of 100. Okay? It is totally, I mean, I covered everything that you are going to be questioned. Okay? Nothing out of the scope. So I believe that your lecture notes is enough for this. Okay? More than that, you don't need. Okay. So we should have a any question on this?
We have a question and answer solving session.
Okay, we will check that at 6 o'clock. Okay. I think not, but we will see. So we will have one just quiz and then.